Good morning, all of you. So, in last class, we discussed about basics of recurrence relation. So, what is the definition of recurrence relation? An equation that can express an in terms of one or more previous terms of the sequence. A0, A1, A2, and so on. An minus 1 is called a recurrence relation. So, we completed some problems on that. In today class, one more problem. We're going to discuss more problems on that. So, first problem, suppose the number of bacteria in a colony triples every hour. In that first question, set up a recurrence relation for the number of bacteria after n hours have elapsed. Second question, if 100 bacteria are used to begin a new colony, how many bacteria will be there in the colony in 10 hours? In 10 hours. So, the question is, the number of bacteria in a colony triples every hour. So, we have to consider that number of bacteria in a colony. Let it be An. So, let An be the number of bacteria at the end of n hours. Okay. So, An minus 1 is the number of bacteria at the end of n minus 1 hours. So, An be the number of bacteria at the end of n hours. So, we consider n minus 1 hours, that will be equal to An minus 1. So, An minus 1 is the number of bacteria at the end of n minus 1 hours. So, since the number of bacteria in a colony, it gives the condition, set up a recurrence relation for the number of bacteria after n hours have elapsed. So, since the number of bacteria in a colony triples every hour, so triples every hour. So, here this can be right in recurrence relation. An is equal to, here An represents the number of bacteria at n hours and it triples every hour. So, that is equal to 3 into An minus 1. Okay. So, 3 into An minus 1. So, this is true whenever n is positive integer. Hence, the recurrence relation for the number of bacteria after n hours is An is equal to 3 An minus 1. An is equal to 3 An minus 1. Okay. So, second question, in that second question, if 100 bacteria are used to begin a new colony, means 100 is here initial condition. Okay, let it be A naught, let A naught is equal to 100. How many bacteria will be there in the colony in 10 hours? We have to calculate the bacteria after 10 hours. How many bacteria will be there in the colony in 10 hours? So, let the given condition be A naught is equal to 100. Then we substitute values for n in recurrence relation. So, the recurrence relation is An is equal to 3 An minus 1. Okay, An is equal to 3 An minus 1. So, we put values for n. So, put n is equal to 1. We get 3 into A naught, that is equal to 3 into 100. So, A2, 3 into A1, that is equal to 3 square. 3 into 100 means 3 square into 100. So, put n is equal to 3. 3 into A2. So, here A2 value is 3 square into 100. So, 3 into 3 square becomes 3 cube into 100. So, and so on for nth term, 3 into An minus 1, that is equal to 3 power n into 100. So, this is iteration formula for the recurrence relation. An is equal to 3 An minus 1 is equal to 3 power n into 100. This is iterative formula for the recurrence relation. Okay, so an is equal to 3 power n into 100. So now we can prove the validity of this equation by using induction principle. So by mathematical induction, we use put n is equal to 0. So put n is equal to 0, relation becomes a naught is equal to 3 power 0 into 100. So 3 power 0 becomes 1. So 1 into 100, that is equal to 100. So a naught is equal to 100. So it gives the value a naught is equal to 100. So therefore a naught is trivially true for n is equal to 0. So similarly we assume that ak is equal to 3 power k into 100 is true. Okay. So we need to prove that a plus a k plus 1 is equal to 3 power k plus 1 into 100 is also true. We have to prove this relation. So now a power k plus 1 is equal to 3 into ak. Okay, from the recurrence relation, that recurrence relation is an is equal to 3 an minus 1. Using this recurrence relation, we put n is equal to k plus 1, we get 3a k plus 1 is equal to 3 into k plus 1 minus 1 becomes ak. Okay, so that is equal to 3 into ak means 3 power k into 100, 3 power k into 100. So it is our assumption. Okay, so bases are equal, we will add powers 3 power k plus 1 into 100. So here we consider a k plus 1, that gives the 3 power k plus 1 into 100. This is true for k plus 1 terms. So a k plus 1 is also true. Hence, by the principle of mathematical induction, an is true for every positive integer n. Okay. So the explicit formula is, so here the recurrence relation is an is equal to 3 power n into 100. So in second question, the question is how many bacteria will be there in the colony in 10 hours. So we have to calculate the number of bacteria will be present after 10 hours. So we consider here when n is equal to 10, we put n is equal to 10 in this recurrence relation, we get the number of bacteria is present after 10 years. Okay, so a 10 is equal to 3 power 10 into 100. So we simplify this, we get 59 lakhs 4900. So therefore the number of bacteria in the colony after 10 hours is equal to 59 lakhs 4900. Okay, so next definition, Fibonacci sequence. Fibonacci sequence. Okay, so the sequence 1, 1, 2, 3, 5, 8, 13. 1, 1, 2, 3, 5, 8, 13 is called Fibonacci sequence. Okay, the recurrence relation for Fibonacci sequence is Fn is equal to, the recurrence relation for Fibonacci sequence is Fn is equal to Fn minus 1 plus Fn minus 2. The condition is n greater than or equal to 2 with initial condition f naught is equal to 1, f1 is equal to 1, f naught is equal to 1 and f1 is equal to 1. Okay, so the sequence 1, 1, 2, 3, 5, 8, 13, these sequence is called Fibonacci sequence. The recurrence relation for this sequence is Fn is equal to Fn minus 1 plus Fn minus 2. So n greater than or equal to 2 with initial conditions f naught is equal to 1 and f1 is equal to 1. So the conditions f naught is equal to 1, f1 is equal to 1 are called initial conditions or the basis. Okay, or the basis. So క్వశ్చన్ లో మిమ్మల్ని ఫెబొనాకీ సీక్వెన్స్ అని అడుగుతారు, సాల్వ్ ద ఫెబొనాకీ సీక్వెన్స్ అని. సో మనం డైరెక్ట్ గా ఈ రికరెన్స్ రిలేషన్ కన్సిడర్ చేసి ప్రాబ్లమ్ సాల్వ్ చేస్తాం. ఓకేనా? So what is the Fibonacci sequence? Fn is equal to the what is recurrence relation for Fibonacci sequence? Fn is equal to Fn minus 1 plus Fn minus 2, n greater than or equal to 2 with initial conditions f naught is equal to 1, f1 is equal to 1. Okay. So next one, solutions of linear homogeneous recurrence relations with constant coefficients. Linear solution of linear homogeneous recurrence relations with the constant coefficients. Okay, so a recurrence relation of the form an is equal to c1 an minus 1 plus c2 an minus 2 plus and so on plus ck an minus k. So where C1, C2 and so on Ck are real numbers and Ck not equal to 0 is called a linear homogeneous recurrence relation of degree k with a constant coefficients. So here C1, C2 and so on Ck are constant coefficient real numbers, and this equation is called linear homogeneous recurrence relation of degree k. So here the degree, how to calculate degree of the given equation means difference between the greatest and lowest subscripts. Here the greatest subscript is n and lowest subscript is n minus k. So the difference of these two, n minus of n minus k is equal to k. So the degree of this recurrence relation is k. That's why here it is given degree. This is a linear homogeneous recurrence relation of degree k with the constant coefficients. Okay, the recurrence relation is of the form an minus C1 an minus 1 minus C2 an minus 2 minus and so on minus Ck an minus k is equal to 0. This is also called a linear homogeneous recurrence relation. Okay, with the degree k. How to calculate the, how to say the degree of the given linear homogeneous equation? So the difference of greatest subscript and lowest subscript. Subscript means here the greatest subscript is n and lowest subscript is n minus k. So the difference of these two subscripts, n minus of n minus k. So n cancel, the degree is k. So the degree of this relation is k. Okay. So see here, a recurrence relation is of the form an minus c1 an minus 1 minus c2 an minus 2 minus c3 an minus 3 and so on minus ck an minus k is equal to 0. Let it be equation 1. So here c1, c2, c3 and so on ck are real numbers and ck not equal to 0. And equation 1 is called linear homogeneous recurrence relation with constant coefficients. So the note points for linear homogeneous equation is the recurrence relation given in equation 1 means this equation is linear since each ai has the power 1 and no terms of the type ai aj occurred. Means here an, the power of an term is 1, an minus 1 term is 1, an minus 2 term is 1, an minus 3 term is 1. So the power of each ai's is 1 and no terms of the type ai aj occurred. అంటే means a square n minus 1 అలాగా ఉండకూడదు. అప్పుడే మనం దాన్ని లీనియర్ ఈక్వేషన్ అంటాం. ఓకేనా? So the degree of the equation is 1, then it is called linear equation. Okay. So the degree of the recurrence relation is k since an is expressed in terms of the previous k terms of the sequence. So degree is the, we already discussed, degree is the difference between the greatest and the lowest subscripts of the members of the sequence occurring in the recurrence relation. How to calculate degree of the given recurrence relation? The difference between the greatest and lowest subscripts of the members. Members means n, n minus 1 and so on. Okay. And the coefficients of the terms of the sequence are all constants. So the coefficients of the coefficients means C1, C2, C3, Ck. These are all only real numbers, constants only, not in n functions. Okay, are not functions of n. So the coefficients of the terms of the sequence are all constants. They are not functions of n. If the function is appear, that is not linear homogeneous equation. Okay. సో రిపీటెడ్ టర్మ్స్ ఉన్న కోఎఫిషియన్స్ ఎన్ ఫంక్షన్స్ కానీ ఇంకేదన్నా టర్మ్స్ వితౌట్ కాన్స్టెంట్స్ కాకుండా ఇంకా ఎన్ ఫంక్షన్స్ కానీ అపేర్ అయితే అవి లీనియర్ హోమోజీనియస్ ఈక్వేషన్ కాదు. ఓకేనా. If f of n is equal to 0, then the recurrence relation is said to be homogeneous. Here f of n represents a total equation. This one, an minus c1 an minus 1 minus c2 an minus 2 minus c3 an minus 3 and so on minus ck an minus k. So this total function represented by f of n. If f of n is equal to 0, the equation is of the form the equation is equal to 0, then the recurrence relation is said to be homogeneous. Otherwise it is said to be non-homogeneous. Okay. So what is the general form of linear homogeneous equation? An minus c1 an minus 1 minus c2 an minus 2 minus and so on minus ck an minus k is equal to 0. This is called linear homogeneous equation with constant coefficients c1 c2 and so on ck. Okay. Ck not equal to 0 with the degree k. How to calculate degree? The difference of greatest subscript and lowest subscripts of the given recurrence relation. Okay. So working rule. How to solve these linear homogeneous equations? So working rule. First we write the characteristic equation for the given recurrence relation of degree k is, so first we have to calculate degree of the given recurrence relation. After that we write characteristic equation for the given recurrence relation of degree k. Okay. So how to write the recurrence characteristic equation means, so we divide the recurrence, so r power k. So the given equation is an. In place of an with the degree k, we write r power k minus c1 r power k minus 1 minus c2 r power k minus 2 and so on ck is equal to 0. Okay. Next, let's find the roots of the characteristic equation. So we get the roots r1 r2 r3 and so on rk. Here three cases are arised. The first case, if the roots are real and not equal, so the roots are real numbers and not equal, means those are distinct real roots, then the solution of the recurrence relation is the given recurrence relation is linear homogeneous. It represented by an of h. So here h represents homogeneous. Okay, an of h is equal to, so if we get different real roots, this is the solution for the recurrence relation, that is c1 r1 power n. Here r1 is root of the characteristic equation plus c2 r2 power n plus c3 r3 power n plus and so on plus ck rk power n. Okay. So in second case, if all the roots are real and equal, if we get the equal roots, equal real roots, then the solution is c1 plus c2 n plus c3 n square plus c4 n q plus and so on plus ck n power k minus 1 into r power n into r power n. Here r is the equal real number. Suppose if we get the root 2 comma 2 comma 2, then the solution of the recurrence relation, how we write? C1 plus C2 into n plus C3n square into 2 power n. Okay, here 2 represents the equal real root. Okay, so in third case, the roots are complex numbers. If the roots are complex numbers, so complex number form is x plus r minus iy. Okay, if we get by solving characteristic equation, if we get complex number, then the solution of the recurrence relation is an of h is equal to r power n into C1 cos n theta plus C2 sin n theta. C1 cos n theta plus C2 sin n theta. So how to calculate R value means square root of x square plus y square. So this is here x is a real part of the complex number and y is imaginary part of the complex number. So R is equal to square root of x square plus y square and theta is equal to tan inverse of y by x. So these are the formulas for roots of the given characteristic equation. So how to solve linear differential equation, linear homogeneous recurrence relation? So first we write degree of the given recurrence relation and then write characteristic equation of the recurrence relation. So we solve that characteristic equation, then we get the roots of that equation. So in that case, we have three cases. So first case is the roots of that characteristic equation is real and distinct. Then the solution is C1 R1 power n plus C2 R2 power n plus C3 R3 power n and so on CK RK power n. So all the roots are real and equal. If roots are real and equal, then the solution is an power h is equal to c1 plus c2 n plus c3 n square plus and so on plus ck n power k minus 1 r power n. If the roots are complex numbers, then the solution of the equation is an of h is equal to r power n c1 cos n theta plus c2 sin n theta. So we calculate r value. So r is equal to square root of x square plus y square and theta is equal to tan inverse y by x. Okay, tan inverse y by x. So problems. Determine which of the following recurrence relations are linear homogeneous recurrence relations with constant coefficients and also find their degrees. So in first recurrence relation is, so here question is which of the following recurrence relation are linear homogeneous recurrence relation with the constant coefficients and also find their degree. So first one, an is equal to 3an minus 1 plus 4a square n minus 2 plus 5an minus 3. Okay. So this is a not a linear homogeneous recurrence relation. So this is not a linear homogeneous recurrence relation because here the degree of n minus 2 subscript is 2. Okay, but this is not a linear homogeneous recurrence relation. The degree of this equation is n minus of n minus 3 is equal to 3. Okay, so going to second one, an is equal to 2n an minus 1 plus an minus 2. Here 2n, the coefficient is not constant coefficient. So this does not have constant coefficient. Kabatti, this is not a linear homogeneous recurrence relation. So third one, an is equal to an minus 1 plus an minus 4. This is a linear homogeneous equation with the constant coefficients. Constant coefficient means these coefficients are 1, 1. So it is a linear homogeneous equation and the degree of this equation is 4. Okay, the degree of this equation is 4. So fourth one, this is not a homogeneous recurrence relation because here a constant term is here. So this is not a linear homogeneous equation and an is equal to a square n minus 1 plus an minus 2. So this is also not a linear homogeneous. Okay, here. Sorry, this is a this is not a linear recurrence relation because the degree of this is 2. So this is not a linear homogeneous recurrence relation. So when we said the degree of the power of equation is 1, then we say linear equation. So the power of this term is 2. So that's why this is not a linear homogeneous recurrence relation. Okay. So sixth one, an is equal to an minus 2. So this is a linear homogeneous recurrence relation with a constant coefficient. So degree is equal to 2. Okay. So here seventh one is not a linear homogeneous recurrence relation because here the function n will be present here. So this is not a linear homogeneous recurrence relation. Okay. So next definition, characteristic roots. Consider the recurrence relation an is equal to c1 an minus 1 plus c2 an minus 2 plus and so on plus ck an minus k. So where c1, c2 and so on ck are real numbers and ck not equal to 0. So the characteristic equation of the recurrence relation, the characteristic equation of the recurrence relation is given above is. So the given above recurrence relation is this one. So the characteristic equation of this recurrence relation is, so we divide lowest subscript. So we divide lowest subscript of the recurrence relation by total equation. So an by an minus k, we get r power k. So minus c1 r power k minus 1 minus c2 r power k minus 2 minus and so on ck minus 1 r minus ck not equal to 0. So in this way we write characteristic equation of given recurrence relation. Okay. So in another way, we how to write the characteristic equation means first we find degree of the given recurrence relation. So here the degree of the recurrence relation is k. So in place of highest term that we write in place of an, we write r power k. In place of an minus 1, r power k minus 1. an minus 2 r power k minus 2 and so on. So here last term constant will be remains. Okay. So ck not equal to 0. Okay. So the solutions of the characteristic equation are called characteristic roots. The solutions of the characteristic equation are called the characteristic roots. So here already we discussed how many cases arise to solve the characteristic equation. 3 cases. Okay. The roots are real and distinct and the roots are equal and the roots are complex numbers. So first problem, solve the recurrence relation. Solve the recurrence relation. The given recurrence relation is an is equal to 5an minus 1 minus 6an minus 2 for n greater than or equal to 2 with initial conditions a naught is equal to 1, a1 is equal to 0. Okay, so this is the given recurrence relation. So first we write the characteristic equation of the recurrence relation, and before that what is the degree of the given recurrence relation? N minus n minus 2. So the degree of given recurrence relation is 2. So the characteristic equation of the recurrence relation is, in place of an we write r square. So minus 5r, okay, plus 6 is equal to 0. So we solve this equation r square minus 5r plus 6. We get the roots 2 comma 3. We get the characteristic roots 2 comma 3. 2 comma 3 are real and distinct roots. So hence the solution of the given recurrence relation is an of h. H means homogeneous, it represents the linear homogeneous recurrence relation. So an is equal to, so these two roots are real and distinct. Okay, so C1 2 power n plus C2 3 power n, where C1 and C2 are constants. We find C1 and C2 values using the given initial conditions. So initial conditions are A naught is equal to 1, A1 is equal to 0. Okay, so we have to find the, this is the solution of given recurrence relation. The solution is an is equal to C1 2 power n plus C2 3 power n. In that we find C1 C2 constant values using the initial conditions. What are the initial conditions? A naught is equal to 1, A1 is equal to 0. Okay, so now A naught is equal to 1 in this equation. So this equation becomes, put a naught is equal to 1, a naught is equal to 1, and put n is equal to 0. So a naught is equal to c1 2 power 0 plus c2 3 power 0. So 2 power 0 value is 1, 3 power 0 value is 1. So the equation is c1 plus c2 is equal to 1. Okay, c1 plus c2 is equal to 1. So next, we put n is equal to 1 in this equation. Let it be equation 1. So it be equation 1. So we put n is equal to 1 in equation 1. We get a1 is equal to c1 2 power 1 plus c2 3 power 1. c1 2 power 1 plus c2 3 power 1. This is not a naught. This is a1. Okay, a1 is equal to 0. c1 2 power 1 plus c2 3 power 1 is equal to 0. So from this we get the another equation 2c1 plus 3c2 is equal to 0. So let it be equation 2 and let it be equation 3. So by solving 2 and 3, by solving 2 and 3, we get the value C1 is equal to, from equation 2, C1 is equal to 1 minus C2. So we substitute C1 value in equation 3, 2 into 1 minus C2 plus 3C2 is equal to 0. So we get the C2 value minus 2. C2 is equal to minus 2. So using this C2 value, we get C1 value. Substitute C2 value in this, we get 1 minus of minus 2. So C1 is equal to 3. So C1 is equal to 3 and C2 is equal to minus 2. Hence the unique solution is we substitute C1, C2 values in equation 1. We get the solution of the given recurrence linear homogeneous recurrence relation, that is an is equal to C1 value. What is C1 value? 3. 3 into 2 power n minus C2 value minus 2. So that's why minus 2 into 3 power n for n greater than or equal to 2. So this is the general solution for given linear homogeneous recurrence relation. Okay. So how to solve the given linear homogeneous equation? First we write the characteristic equation and find the characteristic roots, and then we find the constant coefficients using the initial conditions. Okay. Next question. Solve the recurrence relation an is equal to 8 an minus 1 minus 16 an minus 2 for n greater than or equal to 2 with the initial conditions a naught is equal to 16, a1 is equal to 18. A naught is equal to 16 and A1 is equal to 18. So the solution, the given recurrence relation is An minus 8 An minus 1 plus 16 An minus 2 is equal to 0. So the degree of the recurrence relation is 2. So the characteristic equation of this recurrence relation, how to write? So r square minus 8r plus 16 is equal to 0. Okay. R square minus 8r plus 16 is equal to 0. Okay. So now we find roots of this characteristic equation. So this is of the form r square minus 2 into 4 into r plus 4 square. So a minus b whole square form. So this equation can be written r minus 4 whole square is equal to 0. So r minus 4 whole square is equal to 0. So r is equal to 4 comma 4. In before problem, the roots of the equation are different. In this, the roots of the characteristic equation is equal. So the solution of the recurrence relation is an is equal to, when the roots are equal, the solution is C1 4 power n plus C2 n into 4 power n, or we can write this equation like an. So, okay, leave it. So this can be written like C1 plus C2 n into 4 power n also. Okay. We have to find C1, C2 arbitrary constant values using the initial conditions. So we put n is equal to 0 in this equation. In this equation 1, we get one equation in C1, C2, and we put n is equal to 1 in equation 1, we get another equation in C1, C2. We solve those two equations, we get C1, C2 values. So first, put n is equal to 0, a naught is equal to C1 4 power 0 plus C2 4 power 0. So from that we get the equation. So here a naught value is equal to 16. So we get the equation C1 plus C2 is equal to 16. C1 plus C2 is equal to 16. Okay. Let it be equation 2. Okay. So C2 into here n value 0. So C2 value becomes 0. So the equation is C1 is equal to 16. C1 is equal to 16. So this will be equation 2. So also A naught is equal to 80. C1 4 plus C2 1 into 4 power 1, that is equal to 80. So we get the equation 4C1 plus 4C2 is equal to 80. We substitute C1 value here. We get C2 is equal to 4 and C1 is equal to 16. So now we substitute these C1, C2 values in equation 1. So hence the unique solution is An is equal to 16 4 power n plus 4n into, so here C2 value is 4. So 4n into 4 power n. So, so 16 can be written 4 square. Okay. So bases are equal, power can be add. So 4 power n plus 2 and minus n into 4 power n plus 1. So in this we write An is equal to 4 minus n into 4 power n plus 1, n greater than or equal to 2. Okay, this is the solution for given linear homogeneous recurrence relation. Okay. So another problem. Find the solution of the recurrence relation. An is equal to 2an minus 1 plus an minus 2 minus 2an minus 3 for n is equal to 3, 4, 5 with a naught is equal to 3, a1 is equal to 6 and a2 is equal to 0. So the given recurrence relation is an is minus 2an minus 1 minus an minus 2 plus 2an minus 3 is equal to 0. So the degree of the equation is 3. So the characteristic equation is r cube minus 2r square minus r. So decreasing, powers are decreasing, r square, r cube, next r square, next r, and last one will be constant. So r cube minus 2r square minus r plus 2 is equal to 0. So we solve this equation by synthesis division. So 1, the roots are r minus 1 into r square minus r minus 2 is equal to 0. We solve this. So this is r plus 1 into r minus 2. So the roots of the characteristic equation is r is equal to 1, 2 into minus 1. 1, 2, minus 1. So different roots. So the solution of the equation is An is equal to C1 1 power n plus C2 2 power n plus C3 minus 1 whole power n, where C1, C2, C3 are arbitrary constant. So we have to find these arbitrary constant using given initial conditions. The initial conditions are A0 is equal to 3, A1 is equal to 6 and A2 is equal to 0. Okay. So when A0 is equal to 3 means we put n is equal to 0 in equation 1. We put equation n is equal to 0 in equation 1. Okay, this will be equation 1. So we get A0 is equal to C1 plus C2 plus C3. So C1 plus C2 plus C3 is equal to A0. So A0 value is 3. So the equation is C1 plus C2 plus C3 is equal to 3. Let it be equation 2. Okay. So next we put n is equal to 1 in equation 1. We get A1 is equal to C1 into 1 plus C2 into 2 plus C3 into minus 1. So the equation is C1 plus 2C2 plus minus C3 is equal to A1. A1 means 6. So the equation is C1 plus 2C2 minus C3 is equal to 6. Let it be equation 3. Okay. So now we put n is equal to 2. So C1 plus 1 square means 1. 2 square means 4. So C1 plus 4C2 plus C3 is equal to A2. A2 value is 0. So the equation is C1 plus 4c2 plus c3 is equal to 0. Let it be equation 4. Okay. So now we solve 2 and 3. We get the equation 2c1 plus 3c2 is equal to 9. Let it be equation 5. So we solve 2, 3. We get the equation 2c1 plus 3c2 is equal to 9. Let it be equation 5. Okay. So after solving 3 and 4, we get the equation 2c1 plus 6c2 is equal to 6. Okay. So after solving these equations, next we solve 5 and 6. So from these two equations, we get C2 value, that C2 is equal to 1. C2 is equal to minus 1. We substitute C2 value in any of these two equations, 5 or 6. We get C1 value, that is 6. Okay. So C1 value we know, C1 value and C2 value. Now we substitute C1 and C2 values in any of the 2, 3 or 4, we get C3 value. So C3 is equal to minus 2. C3 is equal to minus 2. So now substitute these C1, C2, C3 arbitrary constant values in solution of the recurrence relation. We get the unique solution is AN is equal to 6 into 1 power n minus 2 power n minus 2 into minus 1 whole power n. Okay. And so here we substitute C1, C2, C3 values in the general solution of the recurrence relation. So 1 power C1 value is 6. So 6 into 1 power n plus C2 value is minus 2 power n minus 2 into minus 1 whole power n. Okay. So next problem. Find an explicit formula for the Fibonacci numbers. Okay. So